In this talk, we discuss about the needs of process models, the two main types of process models, and the two main approaches to dynamic modeling. Now, to start with, why do we even need a dynamic model? There are different uses of dynamic models. In the context of control, the controller needs to know how the output responds when there is a change in the input. Now, this information can be given to the controller in two ways. One, the controller can be designed based on the dynamic model, meaning they're using the model parameters. So that's the case for PID controller. Controller parameters are obtained from the model parameters. In some cases, the controller can directly provide the prediction of the output to the controller. That's the case of model predictive control. Predictive control uses the prediction from the model for the purpose of control. Now, in both cases, whether you design the controller using the model parameters or you use the prediction for the purpose of control, we need an explicit model of the process. So those are the two main uses of dynamic model of processes in the context of process control. In this session, we'll look at the two types of models commonly used in the process industries. We'll take the example first of a distillation column. We know that the top composition from the distillation column depends on the reflux flow. Now we can denote it by reflux rate, reflux flow, reflux ratio, whatever way it's defined for that particular process. Now if you look at the relation between the reflux flow and the top composition, you can express it as relation between reflux rate and the top composition. If you draw the diagram, maybe you'll get some, depending on the process itself, you'll get relation something like this one. Now this curve describes the relation between the reflux and the top composition at steady state condition, meaning that at a steady state, if the reflux flow is this much, what will be the top composition? Or for another case, when the reflux flow is this much, what will be the top composition for this case? Now this relation tells you the steady state value of xd corresponding to the steady state value of r. However, it does not tell you if you change the reflux ratio from this initial value to the final value, how this top composition is going to change. The same thing you can think about the reactor problem. We know that the temperature inside the reactor, this will depend on the flow rate of the coolant. Now if you draw the relation between coolant flow and the reactor temperature, you may get a relation something like this. So this relation will tell you if you have a steady value of coolant flow of this much, the temperature inside the reactor at the steady state will be this. And if you have a coolant flow of this much, the reactor temperature will be something like this one. However, this relation does not tell you if you change the coolant flow from this value to this value, how this reactor temperature is going to change. So this relation, we call this to be the steady state relation. So this is the steady state relation between reflux flow and the top composition. Now the other type of relation that you may want to get is if you change the reflux rate from one value to another, how this top composition is going to change, how fast is going to change, what will be the path for going from one value to the other. So what we're trying to get here is that if with time you change the reflux flow from initially it was at one value, you make a change to another value. So this represents your R. How the XD is going to change from its initial value to the final value. So if the XD had an initial value something like this one, whether it's going to change like this or it's going to change slowly like this. So you need to know how this XD is going from its initial value to the final value. So this information is important for control simply because, for example, you take the example of driving. If you're merging from a connecting road to the highway where the speed limit goes to 60 to 100, and if you go from 60 to 100 in 10 minutes, that may not be indicator of good driving. The same way, if you're changing the reflux flow for a distillation column and the top composition is changing in say half an hour, that may not be an indicator of good control for that particular process. So you need to know how this output variable changes dynamically with the change in the input. So this is what is called this dynamic relation. So this is the steady state relation or steady state model, and this is the dynamic model. So the model that can capture this relation, that will be the dynamic model. So here see that here the key element is the time. So the model should have an element of time where the output will be expressed as function of input and as a function of time. For the steady state value, we get the output as a function of input, but the time variable is not there. Similarly, for the case of this reactor, we need to know for the purpose of control, if there is a change in Fc with time, say Fc goes from one value to another, how this reactor temperature is going to change. So if you plot T as well, and initially the T was supposed at this value, how it's going to change from here to the other value, that is going like this, or it's changing slowly like this. We need to know this behavior. So again, the steady state relation will tell you the relation between temperature and the flow rate of the coolant. The dynamic relation will relate the temperature as a function of time to the coolant flow rate as a function of time. So this is what is called this dynamic relations. So we see here that we can get a steady state relation between the input and output. We can get a dynamic relation between the input and output. Now do remember that the dynamic relation will able to capture the steady state relation as well. So you see that when the output is in transition, that relation is captured. Also when the output is at a steady state, that relation is also captured by the dynamic model. So the dynamic model captures the steady state model as well. So we have seen these two types of model, steady state models and the dynamic models. For the purpose of control, we'll need the dynamic model. Now how to get a dynamic model? We'll take the example of a simple tank process where we're going to find a model relating the level of liquid in the tank to the inlet flow to the tank. Now for this case, we can start with writing the conservation principles. So that's our approach 1. So in this approach, we'll simply write down the conservation principles to get a model. So in doing so, we write the conservation principles: accumulation equals in minus out. I'm writing in the short form, meaning the accumulation of mass equal mass in minus mass out. And we'll write it down and further simplify. And we'll see later that we can end up getting a model of the form so here this HT is the output, this is the input. So we always try to find an input-output model. So this together we get our variables in the model. And we have the parameters here, B and A. These are the parameters. We have the relation between the variables and we have some parameters in place. Those relates the variable. We'll later see that these parameters are nothing but function of the properties of the system, meaning it can be the properties of the equipment or components, it can be the properties of the valves, it can be properties of the fluids, and so on. So those properties of the systems and the variables of the system are related by this equation, and this is what we call a dynamic model of the process. So using the first principle approach, meaning using the laws of nature, we can find a model for the process. Then how to really validate this model, whether it's valid or not. So validation, what you can do, you can get some data from the process, and if you have, for example, you made a change. So you made a change in the valve opening, something like this, and the level changed something like this one. So you can say that, okay, you can use the solution of the model to predict the value of the output using the value of the input. And if you see that the model gives something like this, so you say that this model is valid. So this is one approach for getting dynamic model for a process. Now in a second approach, we take a look at the problem from a different perspective. So you said that at the end, the model can be used to predict the output behavior for a known input behavior. Now, if we initially get a set of data from the process, set of input output data. So for example, you make a change in the inlet flow, something like this one say, and you observe the outlet behavior of the process. And you have this data set. So this is your HT and this is your FIT. Now, using the first principle, if you get a model and the model can be used to predict the output behavior. Now, can it be done that using the data, we can get the model itself? Meaning that can we estimate the model parameter by using a equation fit problem? So that's the model fitting problem. So for this case, we need to know the structure of the model. Now the structure of the model can be obtained from the data, because if you look at the certain type of behavior of the output, you can say that, okay, this behavior belongs to that particular category. Or you can use the process knowledge to get the structure of the model. Once you get the structure of the model, you can really formulate as a mathematically model fitting problem to estimate the model parameters. So using this data, what you are trying to do, you are trying to get the model. So once you get the structure, model fitting problem will give you these two parameters. So this is the second approach to get the model. Now from there, how to really validate? So for validation again, we get another set of data. Typically not the data set that we use to get the model. We get another set of data and again look at the prediction of the model for that particular set, and if the prediction of the model matches the data set, we say that model is validated. So for both cases, you have the final result is the model itself. Here for this case, we have the model, and here this case we have the model as well. The difference is that for this case, we got the model using the laws of nature, and for the second case, we got the model from the process data. This approach is what is called this first principles modeling, and this approach is what is called this system identification. Again, for both of the cases, the final outcome is a dynamic model for the process. So we'll later see that both approaches are useful. For some complicated process, for example, a distillation column, we may end up getting a very large model set to describe the process behavior. However, for the purpose of control, we need a simplified model. So you see that how you can obtain simplified model using the system identification approach. So for our course, we'll extensively use the first principle approach to get the model for different processes. At the same time, we'll use the system identification approach for the real setup used in the lab to get the model for the process. At the end, for both cases, the outcome is a dynamic model of the process. Again, we have the two approaches, the first principle modeling and the system identification approach. So these two approaches are summarized here. Both the first principle approach and the system identification approach start with the objective. However, for the first principle approach, we use the natural laws, or which are also called the first principles, and we gather the process knowledge. Together with the process knowledge and the natural laws, we get a model with its structure. Sometimes we need to simplify the model to obtain a simplified structure. And we get the model parameters from process knowledge. And the simplified model structure is used to develop model parameters using process characteristic parameters. Now both together gives the process knowledge, and from there we can get the prediction and we can use it for validation. So this is the first principle approach in summary. On the other hand, for the system identification approach, we first obtain the process data. However, we need some process knowledge as well. So from the process data, we can get the model parameters, and also process knowledge is used to get some model parameters. Now, model structure can be obtained from process data and also from the process knowledge. So the behavior of the data often shows that what will be the structure of the model, and also we use the process knowledge to determine the model structure. Now together, model parameter and model structure give us the detailed process model. And then we can use the model for prediction, and also using the prediction, we can validate the model. So this is the summary of the system identification approach. So in summary, we have two approaches, the first principles modeling and the system identification approach. The main difference between these two are that in the first principle approach, laws of nature are used to obtain the model. For the system identification approach, process data are used to get the model structure and the model parameters. Now let's try to find out a model for this two-pole process that you commonly refer to as the Wheelsham-Drum problem. So for this case, really, we can write down the conservation principles. And we know that the conservation principles can be written as, in simpler term, accumulation equals in minus out. And you should consider this in terms of the mass, meaning the accumulation of mass equals mass in minus mass out. Now for this case, you can think about this. For pool 1, mass will be given by, if you have the volume given by A1 H1, you multiply it by density, you get the mass, and rate of accumulation will be given by d of mass over dt, and mass in will be given by F1I is the flow in, multiply by rho, get the mass, and again F1O is the flow out, multiply by rho, get the mass out. Now you see here, for this case, the level of liquid in the pool is constant because the flow is from the top only due to overflow. So the level of liquid in the tank is constant. Also, like the area is constant, the density is constant. So this inter terms becomes 0. And this equation really simplifies to F1I equals F1O. Then whatever comes in goes out. So that's for pool 1. Now for pool 2, you can same way you can write the accumulation of mass. So it will be rho A2 H2 d over dt will be, there are two inlets here, so we'll have rho F1O plus this one rho F2I, and there is this outlet rho F2O. Now for pool 2, rho A2, these are constant, H2 is variable, so that's the function of time. So we'll have rho A2 dH2T over dt. So this all can be function of time. We'll write at T. All this multiplied by. Now if you can further simplify this, you end up getting A2 dH2 over dt F1 naught T plus F2I naught T minus. Now because this flow is due to gravitational force, we'll have some constant times square root of H2T, because the outlet flow will depend on the H2, and the relation can be given by CH2T. We'll use C2 here to indicate the second tank. So if you can further simplify it and try to write it in a standard form, you will get so this is the model equation for pool 2. So for pool 1, we get this equation. For pool 2, we get this equation. And this together will formulate the model for the process. Now here really we started with the modeling exercise with defining anything. What do you really want? What type of model we want? So we end up getting something for the pool 1, inlet equals outlet. For the pool 2, we see here there is a differential equation available here, but we see here there is a nonlinear term, and what exactly is our input variable, meaning that which variable we want to manipulate to maintain the level for this case. So we didn't define any of those, started writing the conservation principles. We ended up getting some sort of model, but is this one that you want? So to develop a proper model, we will need to go through some step-by-step procedure. Now this is a simple example, and we started with this simple example, and we ended up getting a model anyway. But think about if I give you the problem of a reactor or the reactor in combination with the distillation column, and they ask you to find the model for the process. Where do you really start? What model we are talking about? And what's the final form the model should be? So for this case, we need to really follow some step-by-step procedure to get the model that we want. That's what I'll call this 5-step procedure for first principles modeling that we'll be discussing in the next session. Again, for a simple process, you can start with writing the conservation principles. You'll end up getting a model. However, for proper modeling, you need to start with what you really want and then get the model relating the proper sets of variable and get the model in the proper form. So that's why the step-by-step procedure comes. Now in this session, we'll talk about the step-by-step procedure for first principles modeling. Now to start with, just to recall that the approach to find dynamic models using the conservation principles along with the principles of thermodynamics, mechanics, kinetics, and other laws of nature, that's what is referred to first principles modeling. Now, as the system complexity grows, we see that how to start a modeling process using the first principles needs to be structured. Otherwise, the system complexity may create problem in the modeling exercise. Now, we'll describe a 5-step procedure for modeling using the first principles. Now, there is nothing magical in the number 5. You can divide the steps in different ways. Just it's easier to remember when you have less number of steps. So considering the steps involved in the process of modeling, found the number 5 to be in one way, describes all the steps, in another way, an optimum number. Now, the step 1 in the first principle approach is to defining the modeling. Now, defining the modeling objective refers to selection of the input-output pair. What's the input you're looking at and what's the output? So this will define the system boundary for the modeling exercise. Now, for particular case, an output can be related to a number of inputs. However, which particular input you are considering, you need to identify. You need to find the model between those input-output. Before doing that, you need to have an understanding of how the variables are related. So the link between the input and output needs to be established. Now, step 2 in the modeling procedure is to gathering process knowledge and information. Now, this step refers to identifying the knowledge regarding mechanics of fluid flow, kinetics of any chemical reaction involved, and if there is heat and mass transfer, we need to know about the mechanisms for heat and mass transfer. Also, we'll need the size and shape of equipment, valve characteristics, fluid properties, and the operational conditions for the process. Now, this information will be very problem specific, and you need to gather all the related information for that particular process. Now, step 3 is the main step in developing the model. It involves the developing the model equations. And mainly in this step, we'll use the conservation principles along with the kinetics, mechanistic, and transfer equations for this case. So all these relations will be put together to develop the model relating the input and output pair. Note that many assumptions are required in developing the model. So you'll have to make suitable assumptions in this step to develop the model equations. Now, step 4 is the simplification and standardization process. We'll see that the model obtained from the first principles may not be usable for the purpose of control. So in many cases, we'll need simplification of the model equation. And at the end, we need to standardize the model equation because for the purpose of control, models of a specific form is used. So simplification and standardization is an important step in the first principle modeling. And finally, you need to analyze and validate the model. So this validation often may require process data, process knowledge as well. So using the data, we can validate the model by comparing the process data and the prediction from the model. Remember that a simplified model remains valid over a certain range of operation only. So user needs to know the range of variables over which the model is valid. So if you develop a model for one range and try to use it for another range of the process variable, the model may not be valid and the prediction can be very different from the real process behavior. So that's in summary the 5 steps approach for process modeling using first principles, which start with step 1, defining the model objective, step 2, to gather process knowledge and information, step 3, to develop the model equations, step 4, to simplify the model and express it in a standard form, finally step 5, to validate the model. Now, what are the different uses of dynamic models? So dynamic models can be used for controller design. The parameters of PID controller are directly obtained from the model parameters of the process. Also for model predictive control, prediction using the process model is used for the purpose of control. So those are the 2 main uses of model in the context of control. There are other uses as well. For example, for process simulation. So to simulate the behavior of the process under different operating conditions, it's often useful to use a model instead of trying to understand the process behavior using the real process. Now, this simulation can be used for monitoring, for failure prediction, and diagnosis. Models can also be used for operator training. For example, abnormal operations can be simulated using model, and that can be used for training operators. Also, the startup and shutdown activities can be simulated using the model. Now, another use of dynamic model is process optimization. You can run the process at many different operating conditions using the model to identify the optimal operating conditions, which is not feasible by using the real process. So these are the main uses of dynamic models. So just to recap, models are used for controller design, models are used for simulation, models are used for operator training, and models are used for process optimization.